The main thing we want to establish here is that there is a relationship between temperature and humidity. And the basic idea is that warmer air can hold more moisture, colder air can hold less moisture. And this is related to relative humidity. So if you think about a given amount of water vapor represented by this circle at 50 degrees Fahrenheit, if the air temperature, let's say, were 50 degrees, and it could hold no more than this amount of water vapor, that air would be at 100% relative humidity. But if you go up to, let's say on the far right, let's say the temperature is 86 degrees Fahrenheit, that air is warmer, so it can hold a lot more water vapor. And that same amount of moisture, represented by this circle, is not 100% humidity now. It's only 28% of the total possible volume. Warm air holds more moisture than cold air. And if you think about the action of molecules, this will make sense. Heat energy, of course, is those molecules vibrating, jumping around. And the warmer the air is, the more those molecules jump around and elbow each other out of the way, and there's more space between molecules. And so there's more room in there for water molecules. So, let's see, if you're at a colder temperature, you can hold the air can hold a lot less water vapor, and so it doesn't take as much for that relative humidity to reach 100%. So that air is completely saturated. And what happens then? You've reached dew point. That's that temperature at which, you go outside in the early morning and there are dewdrops all over the blades of grass, or you're out camping and you wake up in the morning and there's water all over your sleeping bag. That's because at a colder temperature, the air can hold less moisture, and so it becomes saturated at a low temperature. It reaches 100% relative humidity. Here's some definitions. The other thing I want to point out is that architects and HVAC technicians use these charts called psychrometric charts, which give them a relationship between the temperature along the bottom axis and the humidity along the vertical axis, and then the relative humidity represented by these curved lines. And this chart, this psychrometric chart, was established by ASHRAE decades ago, and now architects and technicians all use these charts to figure out where is the optimal level for temperature and humidity, and at what point does it feel moderately comfortable, at what point is it hot and humid and too muggy, or hot and too dry. So that's all I want to say about these. There are quite a few slides in this slideshow after this one that will walk you through a little bit how to use these psychrometric charts, and then in the last slide there's a book by Ogilvie who goes into quite a bit of detail about how to use these charts. But for now, we'll just know they're a thing, and going back to the beginning, warm air holds more moisture than cool air. The warmer the air, the more moisture it holds.